Welcome to AP Review number 3 solutions. Two problems here. One is actually a projectile motion problem. That's the second one, even though it looks pretty complicated, it's not. And the first one is another problem involving forces, force diagrams. And important here is understanding of systems, because that's a big thing for the AP. So we hopefully haven't forgotten the good old Atwood machine. You don't have to know the name, but we have two masses over a pulley, and we have competing forces in terms of tensions. Now, they don't ask you to draw a force diagram on these, but they're pretty important in order to figure out the problem. So in this one, we want to derive an equation in terms of speed, okay, for this one as it falls. So this is, in a sense, kinematics, and we got a velocity, we know a distance, we don't know a time, so don't try to find time. Distance is sufficient, and implicit in this, because of the forces, is there's an acceleration. So the equation you're ultimately going to want to use is v squared is v naught squared plus 2a times d. All right, so the trick is to find the acceleration. To find the acceleration, you got to understand the forces. Now, you can do a force diagram. Nothing wrong with that. You got limited time. You can take shortcuts. I'm going to go through the full one. You know we have tensions pulling up on the strings, and then we have mg, and we have 3mg. Okay, I'm going to cut to the chase there. Don't worry about the size of the arrows. I think I've done them right. Anyway, what we want to recognize is if we're looking at both masses that are moving as one, we want to treat our system as not one block or the other, but both blocks. So we count all forces. And if we count all forces, we see that the tensions cancel out. They're in opposition to each other. So in other words, our acceleration, which is F net over m, okay, we can do this fairly quickly. If you recall, the forces here, as I did here, is nothing more than 3mg minus mg all over m. The m's cancel out, and we're left with 2g. Okay? No, that's not. I'm sorry. Silly mistake. All over 4m. Silly me. All right, so we have 3mg minus m, which is 2mg over 4m, and we get 1/2 of a g. All right, we expect that the acceleration has got to be some fraction of g, and there we go. So we put that in here. We know that v naught is 0, so v squared equals 2 times 1/2 g, or g times d, so v is radical gd. All right, that's pretty straightforward. Remind you, don't mess with time if you don't have to. It just makes it unnecessarily complicated. So the next problem, and this is, I believe, if you look at the rubric, is 4 of the 5 points for this. Okay, excuse me, 4 of the 7 points for this problem. And that's the reason I point that out to you is you look at the work you had to do, you know it's going to be multiple points, especially for the number of steps you had to take. So that's important for the next two problems in the sense that in the next two problems they're not going to be as involved because there's only 3 points left. And so you might think, oh, this is really complicated, when in fact it can't be, just based on that. So that's just a little tip for you when you're taking a test, is gauge how many points each problem is most likely worth, so that you can A, prioritize, and B, maybe have a hint how much it is. All right, so B, it says determine the work done by the string on a 2-block system. So again, very careful reading. It's not work done on the blocks. They got to be more specific. It's done by a specific thing, the string, as opposed to, let's say, the earth, and the 2-block system. So it's not one block or the other, but rather, excuse me, both blocks. Okay, so there are, if I go back to the diagram, okay, let me just get rid of all this. I want to know the work done by string, that's due to the tension, so that's the forces. And work is a force times a distance. So I've got to calculate that twice, one for the one string and one for the other string. Well, it shouldn't take too much to figure out that the work done by one is equal to the work done by the other, but it's going to be in the opposite direction because the tensions are in opposition to one another. So it took me forever to erase that. But in other words, if the system is moving downward, okay, so that's the general motion that way, then this is doing a work, let's call it the work due to the 3, is negative t times whatever distance it moves, in this case d. The negative is because the tension is in the opposite direction of motion. The work done by this string, okay, this is moving up, so the tension is in that. The work done by the 1 mg, I'll just call it the m, is positive t times the same distance, and so when we add it all up, we get 0. So long story short, for 1 point, that problem is no work is done by the string. And that we can look at that from a different standpoint, in that the strings are internal forces to our system if our system is defined as the 2 blocks. So internal forces can't do any work. All right, and then 3, it says the acceleration in the center of the mass of the block string system has a magnitude of a center of mass, and explain why it's not g. In other words, why isn't the whole system in free fall? And if we ask that question in terms of one mass the other, that's probably a little easier to do, because I could say, let's say for the small mass, it's not in free fall because there's another force on it, tension. I could say the same thing for the 3 mass one. It's got gravity acting on it, but there's tension opposing it, so they can't possibly be in free fall. But they didn't ask for either one, they asked for the system. So if you're in free fall, and this is a statement you'd make, you have the only force can be acting on you is gravity. So is gravity the only, so I'm just going to draw a generic dot for the whole system. Is it just mg? We know it's not, because we just solved for the one block, the other is half of g. So there's got to be an external force. The question is, where is that external force coming from? If you understand that it can't be the tensions, because the tensions are internal to it, we need an external force, then it's got to come from the pulley. Okay, so the pulley itself is exerting an upward force on the system, preventing it from being in free fall. So that's the quick and dirty solution to that one, for 2 points. 1 point for saying that the external force is coming from the pulley, and the second pointing out that the F net then is not just mg, but it's the mg minus the pulley force. Okay, so let's move on to the next problem, which is really just a free fall problem. All right, so here's another 7-point problem, 13 minutes. We're tossing a toy up in the air at an angle, and the toy is going to rotate around and around. And you might think, oh boy, this is rotational motion. Actually, it's not, because they're not really asking anything about the rotation. They just want you to understand is, even if we have a complicated set of motion, what's the role of gravity in all this, and free fall, and then that makes it fairly simple. So we just want you to understand that where we introduce free fall with just a simple object like a ball or a cat or something like that, just because we replace it with a rotating 2-ball system really doesn't change anything in terms of forces and therefore how things behave. Okay, so they want us to sketch how the components of motion will change as it goes from the person's hand back to their hand. But it's not going straight up or down, it's at an angle, and they make that clear. All right, so what you got to recognize is horizontally, so it's going to take a trajectory of like this. It's just going to do an arc. Yeah, it's going to spin as it's going around, but the key thing is the whole system, the center of mass, if you will, must follow the parabolic arc, because the only force acting on it is gravity. So we hopefully recognize that horizontally it's always moving. So it doesn't matter which point you choose here, you just got to draw a flat line to TF. Anything after they're going to ignore. Okay, so I could have put here, here, here. I don't think they'd worry about whether you put negative. I mean, it's arbitrary whether you call it positive or negative, but safe to go with positive. All right, the vertical is just a little bit more complicated because the velocity is slowing down to a stop, and then it's gaining speed in a symmetric fashion. So we want to ask ourselves, is at time 0 when it leaves the hand, right? So it was launched this way with some velocity v. We already established that Vx is constant. We should understand that Vy is changing with time. So it left a hand with some velocity Vy, upward we're going to call positive, and then it's slowing down to 0. So at some point it's going to be at 0. Actually, if I want to be accurate, and I was accidentally, I want that point of 0 to be halfway between the initial and the final. Okay, the question is, how is it slowing down? It's slowing down linearly because it's just accelerating at a constant rate. Then when it gets to the peak, it's going to start falling at the same rate, but falling in a negative direction. So we got to be careful not to make this a V, but to continue along in a straight line to right there. In other words, this should be a continuous line because the slope is 9.8 or negative 9.8. We don't want to put a little kink in here to indicate some change in acceleration. So easy to make a mistake on that, but this is fairly straightforward in terms of any projectile motion problem. Okay, now they get into the part where it's rotating around and see if you understand how to deal with that. So the first one is draw a force diagram for the left sphere only when it's at the top of its trajectory. Okay, so on the left sphere, there's definitely gravity pulling down on it, and that's always straight down. Is there anything else acting on a sphere? And the answer is yes. There's going to be tension coming from the string that's holding them together. Okay, so it's as simple as that. We don't have to worry about breaking this components. We're not interested in the right sphere. Technically, the left sphere is pulling the right sphere. So if they were to ask you about the right sphere, you'd have this and you'd have that, very similar. Now they change it to our system is the center of mass of the two. Oops, I already did the left sphere right here, actually. Okay, I already did this one. So let me go to the whole toy. Okay. So don't do this, but here are the two spheres, right? We had this and this and one I just showed you, but these, we want the whole system, right? And in the whole system, right, the only thing that's acting on it is gravity. Okay, because the tensions are internal, we wouldn't want to include them. We want the external forces on the whole toy, the spheres and strings system. Okay. Lastly, now this becomes a problem where we calculate. They fire it up at an angle of 60 degrees, 15 meters per second. Calculate the speed at the center of the string. Okay, so it's important that we only carry about that. That's the point of this one. The whole toy, if the only force is the gravity, okay, then we don't have to worry about any of the rotational part. That's for the individual spheres. Anyway, where do we want to calculate this? At the reaches the top of its trajectory. So what's the significance of reaching the top of its trajectory is that it's not moving vertically anymore. In other words, all its motion is still horizontal. So it's easy to say the velocity is zero, but it's not. It's always moving horizontally. So to get 2 points for this one, you just basically have to say that the v at that is vx, and some indication you want to find ux, and that would be equal to the original launch speed times the cosine of the angle. So you would just put in 15 cosine 60. Cosine of 60, I think, is a half. Sine of 30 is a half, yeah. So you should put 7.5, and don't forget units. For whatever reason, they're counting units on this one. Okay, so that sums up those two problems.